Hello everyone, what's up? Today we are going to go through this paper, hopefully deeply enough, called Rethinking Action Spaces for Reinforcement Learning in End-to-End Dialog Agent with Latent Variable Models. This paper was published in North American chapter of ACL in 2019, and it's a collaboration between Carnegie Mellon University and Shanghai Jiao Tang University. Hopefully you are going to enjoy it. By the way, my name is Mushtaba Walipur, and I'm a PhD student at University of Waterloo at Data Analytics Lab. Today, the outline is, first I'm going to introduce you the problem, and then we are going to just maybe have a better idea what was their solution, how they actually, what was their contribution, and how they just tackle the problem. And in the end, we are going to see some experiments, and that's it. So the first question is, what's the problem and why this is a problem? So in this paper, the main goal is to redefine the action space that we usually use in reinforcement learning based conversational agents. And they want to reach a better action space that can help them to overcome with the current limitation that we have in this kind of problems. This paper generally introduces a new framework to solve any end-to-end dialogue agent settings, but to just get familiar what kind of problem we can see in this dialogue agents. I just provided two sample example. Okay, as you can see in this problem, in this specific problem, multiple scenarios. So in each scenario, the available resources can be different. So as you can see here, in the first scenario, there is only one book, one hat, and 3 balls available. But in the second scenarios, there are 4 books, 1 hat, and 1 ball available. And as you can see here, also the goal of these two entity, the agent and the user, can be same as the first scenario. It can be different, as you can see in the second scenario. And there is going to be up to t times. So let's say that our horizon is going to be t, and there's going to be t times a conversation between the user and the agent, and in the end they have to reach an agreement if in a very limited, in a limited time at least. It's not going to be, this t can be infinite, but we are going to limit our horizon. And if they reach in that specific time horizon to an agreement, then they are going to receive some reward. Okay, so this is one example that we can use, that we can have some kind of AI agent to hopefully just negotiate with someone else and reach a specific agreement, constraint, satisfying some constraint that we have in our mind. Usually when you have, if you're familiar with NLP, usually if you have sequence as input and also as output, you're going to use a very specific neural network structure called sequence-to-sequence network, which usually it is based on encoder-decoder structure. So, given a context vector, the encoder is going to encode that context vector to something useful, hopefully for the decoder. And the decoder, if it is an autoregressive decoder, then it's going to generate some character for you. If it is character level, or if it is word level, it's going to generate one word at a time. So it's going to, this decoder that I just show you here, first it's going to generate the first word, and given that first word, I will pass that to the decoder again, and the decoder is going to generate the second one. And just let's say that we are going to generate up to n words here. Okay, and we will call this later, you will see that we will call this u1, the number of words that is in the first line is going to be u1. Okay, if we because we doesn't know necessarily when these two agents are going to reach an agreement, we are going to recursively pass this new context vector again to the encoder, and then the encoder is going to generate hopefully a good a good context vector, a good information vector for the decoder, so decoder can generate some useful words for the next turn. So if I want to show you in that settings, let me just delete this thing so you're not going to become confused. In the next turn, it's going to be something like this. Just consider that this encoder and decoder are similar. I just want to show it, maybe a better way. Just open that. And as you can see here, I just update the context vector with the encoded version of the information, and also so the output of I just use the output of the encoder and the output of the decoder in the previous turn to just have a new context vector here, and then I'm going to pass this context vector to the encoder, and the encoder is going to give me a specific vector that I'm going to pass that to decoder, and decoder is going to generate another M words for me. I can continue this procedure up to T times. Okay, so if you are considering these settings, you might be able actually to guess that we can use this, to maybe maximize a specific log probability. So, we can use this kind of a structure to solve a supervised learning problem. Okay, because just imagine that you have a bunch of these different scenarios, and you know that in the end, in each step, you're going to have that specific word. So if I have this, let's say we have this, I would like the hat and 2, then the probability of balls is going to be much higher than anything else, hopefully. If you just learn and imitate from the humans, and mostly, let's say that when your humans just use that combination, so I would like the hat and 2, then most probably the next word is going to be balls. Maybe a better example is going to be something like, if I can see, for example, here I have to have the hat, maybe when I use I have to, or when I use I have, probably the most probable words after I and have can be 2. Okay, not necessarily always, but we can say that, okay, the probability of being the next word as 2 is going to be high. So if we just maximize this expectation, then actually we can imitate the human agents, and we can solve this kind of problems, as you can see here. So there are already many solutions with supervised learning in these settings, but it seems that reinforcement learning can also perform very well, and we also have a reward signal, so why not to use reinforcement learning? Okay, so if we had some simulator that just provide us the reward signal, we can use those reward signal to just update our weights in decoder and encoder. And if you are familiar with the reinforced algorithm, then you should be able to see that the gradient objective function for the RL is going to be similar to this one, considering that you have in the first turn you have U1 word, in the second you have U2 words, and in the T turn you have UT words. Okay, so let's say that for T turns, and for each turn we know that we have which words. Okay, let's say that we have U1 words for the first term, then you are going to calculate this this term. And as you can see here, we just multiply the reward by the gradient of the log probability of the current word given all the previous words and the context. So as an example, let's say that we are in turn one, and in turn one, obviously we have n words, and let's say that we just generated, currently we are going to generate the second word. So as the second word, we have obviously a context vector and also just the W1 here as W, as this term, and then we are going to calculate the probability of W2 given W1 and the context vector. And then we can calculate the gradient, and based on that gradient, we can optimize our decoder and encoder weights. But as you can see, this is not going to be necessarily an ideal situation because, or there is two major problem at least. First, if you are going to, optimize this network in word level settings, then at least you have to consider, because the number of words usually in human language are very large. So maybe, okay, let's say that we just consider the first 50,000 most probable words in that, in this problem, and then your action space is going to be very large. Even if you just limit that to 50,000, it's still large, and another big problem that you might have in the reinforcement learning settings, it is actually a very long horizon. If you just consider this horizon, just a signal in the end is not going to be that helpful to find, the probability of each word and to update, this term. You're not going to achieve very interesting results, at least not necessarily always. Because of these two problems, they just wanted to rethink this action space. So, hopefully have a smaller action space, and they can also maybe limit this horizon somehow, at least in their, in this expression, and then maybe we can somehow design better reinforcement learning algorithm for this end-to-end dialogue agents. Considering the previous slide, we might be able somehow, with combining both supervised learning and reinforcement learning, solve that problem up to some extent, but not necessarily perfectly, as they did already in many other papers. But in this paper specifically, their goal is to tackle those two major problems that I just mentioned in the previous slide. So, they propose a framework called Latent Action Reinforcement Learning, LARL. And if I want to give you an idea, what's briefly, in brief words, what they actually solve, what they just propose us is that how to discretize the action space without, without losing the expressivity. So, we want an action space that's expressive enough, but also is not that, large maybe. Yeah. So, we can use that reward signal to just optimize our network. As the first important modification, they just use variational inference. So, in other words, they just, instead to use directly the output of the encoder and pass that to the decoder, they just introduce a latent variable, let's say called Z, and using that Z, we can absolutely calculate the probability of the next word given the context by calculating the probability of the next word given the latent variable multiplied by probability of latent variable given the context. And as you can see here, the goal is, instead to update the both weights for decoder and encoder, they just wanted to change the action space to the latent space. So, they can have absolutely much more efficient action space. So, the action space is much more smaller than the previous model. And as you can see here, also your horizon is not anymore dependent to the number of words that you just generated in each turn. And as you can see, just with this very simple and neat idea, they just solve both problem, and we can still use the same reinforced algorithm to update our model. But the question now is that what kind of latent action we can actually use, which one is more suitable. And as usual, we are always using a prior like Gaussian, and we can also use a categorical distribution to model this kind of problem. So let's see which one is better. So usually in variational autoencoder, we are using Gaussian distribution as the latent variable. So as you can see here, we just rename the output of the encoder as H. So the F is our encoder, and it's going to receive the context vector just like the previous slide, and it's going to give us a vector H that we are going to use and pass that H to another function, let's say pi, and this pi is going to give us the parameter for our distribution. So it's going to be the mean and variance for a Gaussian one. So you can see here, then we can absolutely using those parameters, these two mean and variance, we can absolutely sample just from this distribution a specific z, and then we can pass this z to the decoder, and decoder can give us some new words. And as I previously mentioned, we can continue this process up to some specific horizon, and as you can see here, we can stop at turn t. The other thing that I just want to emphasize is that we are going to update just the weights for the encoder, not the decoder necessarily. So as you can see here, the decoder is going to be intact, and as usual, we can use the same objective function that we had previously in our reinforced algorithm without any specific change. But you have to also notice that already that we can calculate the probability of word given the latent variable by just using the decoder weights, and also we can calculate the probability of z given the context vector. That actually we need this one by sampling from this distribution, and we can then use this one to opt our weight for the encoder. It seems that it is useful to somehow maybe simplify the latent action space. So they just, use the categorical distribution instead of Gaussian distribution. So they assume that they have an independent k-way random variable, and after we just calculate the output of the encoder, we can pass that to some function that give us some vector with size k, and we can actually use those vectors to calculate a distribution, and then we can sample from that specific categorical distribution to map that vector, that one to embedding vector with using a specific token embedding, and then as our output we are going to have m different vector with size d. So the output of this procedure is going to be m by d, and then we can pass this to the decoder, and then just like before, we can continue this process up to time t, and then we can based on the reward that we are going to achieve, we can update the weights for the everything before latent action. So still we can use the same expression that we just used in our reinforced algorithm. The only difference might be due to the fact that how we can calculate the now probability of z given the context using m different vectors that we have as the output of our procedure as the latent variable. So they just use this expression. As you can see here, this expression can help us to just find a gradient to update our weights, and then we are going to, as usual, we are going to solve the problem. But still, there is a question that you might ask, and let's assume that we can actually somehow pass this, in this m different vector to the decoder, and decoder can perfectly work. The question is that, is this, using this m independent k way random variable are expressive enough for human language model? If you just simply calculate how many different unique combination you can have with those m independent k way, you're going to exponentially have a k by the power of m unique combination, which absolutely I can say it is expressive enough for a human language model. However, we just assume that we can pass, this m by d matrices to the decoder, and decoder can generate some new words for us, and we can be happily, happy ever after, or something like that. But actually, it's not possible, because the decoder initial state is a vector size by d, but our output as a latent variable for now is just a matrices m by d. One easy solution, absolutely, it can be always summation. So they call this technique summation fusion. So they just sum all of this vector together. But there is some problem with this approach, as they claim in this paper. So you're going to lose absolutely the order information, which something which usually it is very important. So because of that, you just have the idea of attention in all the NLP. And this is not going to work perfectly with long responses. So, as another contribution, they just use attention, and they call this method attention fusion, to just somehow find a way to pass this m by d matrices to the decoder. So they just use the attention vector, and as you can see, we just introduce to the output of the context vector, we just use a weighted sum of this summation. And now the problem is that how we can actually calculate this, this alpha of mi, which is the attention weight. How we can, somehow update this one, how we can calculate them. They exactly use the same idea that usually we use in the whole attention paper. I'm not going to go into detail, but actually, if you check the same attention original paper, you will see that always we are going to compare our current hidden state, which here I just use the hidden state of the decoder by h of d, in each step index during decoding. Let's say that in the step of I, we are going to compare our current hidden state with our future hidden state, and we can actually calculate some weights for alpha, and then we can pass this, using this alpha, we can actually calculate the context vector, and the context and the current hidden state can give us an approximation for maybe the next hidden state, and then we can use that hidden state to update or and then next hidden state. And we can also use this one to just predict the next probable words. No, the last part of the puzzle is about absolutely optimizing, how we can optimize this kind of network. Let's imagine that everything here is, differentiable, so we don't have any problems. So, they, in their paper, they just use Gumbel softmax for categorical distribution and reparameterization trick for the Gaussian distribution. So just let's, assume that we don't have any problem with the differentiability. So, usually in variation autoencoder setting, we are going to, because calculating the marginal distribution is not intractable. So instead they optimize the whole the whole expression. They just use evidence lower bound to somehow optimize the problem. So here they did the same, but they found out that actually if they use this full elbow that you can see as here, which there is two terms here, a reconstruction error that you're going to just maximize the probability of x given the latent variable, and also you're going to decrease the distance, the divergence between these two, the posterior and the probability of the latent variable, the context. So let's assume that we have a neural network that just, somehow we can actually approximate this posterior Q as, latent variable given the X and C, and we can then use this regularization term to just, optimize our neural network. The problem is going to be because in the training we have maybe we have access to those approximation, this posterior, then we might be able to actually use this Q. But the problem is that in the setting we don't have access to posterior, so we have to use directly the distribution of Z given the context vector. And they call this problem as the exposure bias because the decoder in the training is only sees Z samples from the posterior distribution Q and just never experiences anything from the this distribution, which we might actually we are going to use in the test setting. So this can be a problem. So they introduce a light version of this evidence lower bound, and this evidence in that setting actually they use as their posterior, actually just use the encoder, the distribution of the encoder. So if you just replace the distribution of the encoder into the full elbow, you will see that you're going to have something like this, which this expression I can see here, the first term is just, nothing really changed here. But in the second term, the version is going to be same, because you just compared the two similar distribution, and then you're going in the end, this should be 0. Then you just without any regularization, you actually maximize this term, which is not a perfect idea. So they actually, relax the problem and they regularize this term with another, just with another divergence. So they just compare this this probability of, this distribution of Z given the context vector with the prior. And as you might know, this prior can be absolutely uniform for the categorical distribution, or maybe even Gaussian for the Gaussian latent space. I just forget to tell you that we can absolutely calculate the probability of Z given context by using the pi and the encoder that we have, and we also we are able to calculate the probability of X given the latent variable by just using the decoder. As the last contribution, they introduce a new metric for this setting, that simultaneously shows their rewards and also the language quality. So imagine that, if you're familiar with NLP, you should know that we want some models that keep the perplexity as lowest as possible. So, so let's say that we have a specific budget for our perplexity, so we have a maximize. So the x-axis just shows our language quality budget by perplexity in this curve that you can see, and the y-axis just represent the task rewards. So as you might be able to guess, the green line is just, the green curve is just our ideal model that we just like that, because it's both maximize the rewards and it has the best language quality. And the red one is actually sacrifice language quality, but it can achieve a very good reward. So it's not an ideal case because we want sometimes some just a reinforcement learning method that both keep the reward as maximum as possible and also keep and respect the human language, not necessarily just model a very odd languages that we can't understand. So the blue one actually is not good because it can't achieve the high reward that we are interested in, but okay, it can respect the perplexity constraint that we have. So it seems that all the past metrics before this doesn't necessarily keep this balance between the task reward and language generation quality. So they just introduced this LCR curve. In the end, I like to also share with you some experiment that they just shows in their paper. So as you can see here, they used a data set called Deal or No Deal, which is just a negotiation data set that contains around 5,000 dialogue based on 2,236 unique scenarios, which they keep just 252 scenarios for testing, and they also randomly sampled 400 other scenarios from the training set for validation. As you can see here, they use the same curve to just show their performance, and as you can see here, the word level reinforcement learning, the baseline, also achieved the max, a very good amount of reward, but actually it didn't respect the perplexity constraint. So also their model, the latent level reinforcement learning, the proposed method achieved a very good amount of reward and also respect that perplexity. So if you just see in numbers, you're going to see that their light-based optimization, categorical distribution reinforcement learning method actually outperform almost in all the metrics that we have here. In terms of diversity of the responses, they also compare the word level reinforcement learning with the latent level reinforcement learning, which, as you can see here, absolutely the latent level just outperformed the word level easily. And so it seems that although the word level reinforcement learning maximized the reward, but it wasn't successful at all to somehow give as the output some humanly friendly language combination or something like that. In another experiment, they just used another data set called MULTI-WOZ, which contains 10,000 dialogues on 6 different domains. Around 8,000 dialogues are for training and 1,000 are for validation and for testing. They use that sort of combination. They just shows that okay, the human as the best one. Just achieved around 90% of informant, and the success rate of the human is around 82%, which, as you can see here, their best model, the light attention categorical model, just almost always outperform all the baselines, and it's very close there. They're actually the performance is very close to the human level performance on this data set, which is very challenging, and the result is very promising. They also shows the same curve for their method, which we can see, all the details here. They also provide, some example that shows that, the diversity of the output of the word level is not really helpful here because, if you just check the context was, given this specific context for this MULTI-WOZ data set, the output of the word reinforcement learning is just keeping those values. It's not really humanly friendly. Just train IDs, leaving value placed on this, on this, on this, on this, on this. Leaving this. It just somehow use I can say just find a bug that if you use those specific train ID value place, value day, train ID, value count, train ID together, you're going to maximize the reward. But as you can see, for the light attention categorical model, the response is very humanly. It seems like a human response. So would you like me to book that for you? It's very interesting that it just generated something like that. They also compare all the models together, for both dataset for deal or no deal and multi-WOZ dataset, to just have the better sense that which model is better. And they also shows that the effectiveness of the using of that KL divergence in the light version of it. If you increase that one, so if you just use 0, it means that you just don't use any regularization. It seems that, as you can see here, it's not that effective. The difference is a lot, absolutely. So, they also shows this similar curves with more detail for all the other combinations. And this is it. I think this is almost all the paper and all the useful things you can find in this paper. Hopefully it's comprehensive. And as the conclusion, just for a reminder, they propose a latent action space for reinforcement learning end-to-end dialogue agent settings, and they also solve a problem called exposure bias by their light version of the full elbow objective function, and also they introduce attention fusion for discrete variable. I like this part of their paper because it was in an unsupervised manner. They somehow create an action abstraction, which is very interesting, I think, and in the end, they just introduced a new state-of-the-art success rate on multi-WOZ dataset, which is very promising, I can say. If you have any question, please don't hesitate to add comment in this YouTube channel. Hopefully, maybe we can find a solution together. And if you find any, thing that I can learn, please don't hesitate to let me know, because I'm still learning and I really like to learn as much as possible. Again, my name is Moshtaba Walipur, and a PhD student at Data Analytic Labs in the University of Waterloo. I hope you really enjoyed this. Please don't hesitate to let me know if you have anything in your mind. I like to hear that, and hopefully you have a great weekend ahead of you. Goodbye.